In the second video for SLO7, we'll be discussing how to evaluate additions to carbonyls that you might expect to be reversible, but that don't involve anionic nucleophiles. So the strategy we used before of looking at anion stabilities is clearly not going to work here. What anions? So first key is that these reversible additions are usually going to involve weak nucleophiles. So we saw some cases where we had water molecules or methanol. We even saw like cyanide, which is kind of an unusual case. It is a good nucleophile, but in a lot of cases it actually is also a reasonably good leaving group. So we know this might be reversible, but we could wonder, well, to what extent? You know, another way of saying that is, what's the equilibrium constant for this hydration reaction? So it turns out we've actually discussed this in SLO4, but that was a long time ago. You know, the world has basically ended since we did that, so I thought we could review. And so what we're going to start to think about is, well, for one of these individual reactions, it can be very difficult to predict. There's very detailed calculation data and thermodynamic data for these kinds of processes, but that's not something that we're going to discuss in great detail. What we could do is look at comparing reactions, though. So if we looked at this hydration of acetone and we compared it to the hydration of some other kind of carbonyl, so I'll choose an aldehyde. We'll use acetaldehyde, so 2 carbons, plus water, and that's going to give rise to an aldehyde hydrate. I could maybe make some decisions about, well, maybe if I could measure one of these values experimentally, I could make a prediction about, well, relative to this reaction, this one is more or less favorable. It turns out, maybe conveniently, but this is real data, I'm not making this up, that the equilibrium constant for this reaction, for the hydration, of the acetaldehyde is almost exactly 1. So we could say, we'll just call it 1 for the sake of discussion. And so now we need to decide, is this hydration going to be more or less favorable than this one? Like I said, we can't analyze nucleophiles. That's not going to be meaningful for us. And in any case, it's the same nucleophile in both of these reactions. But we can see that the carbonyls are different. And so in SLO4, the way we discussed this was to think about which of these 2 carbonyls was more highly stabilized. You're good at this now, and so you'll be able to very quickly look at this structure, identify that you have 2 different hyperconjugative donors to the carbonyl, which is going to make this carbonyl more stable. So if this is a more stable carbonyl than this one, why would I hydrate this as much as I do this one? And in fact, I don't. So if I measure the equilibrium constant here, I'm going to find it's about 10 to the negative 3. So quite a bit smaller, about 3 orders of magnitude smaller. And so what we're seeing here is that rather than looking at nucleophiles, in some cases we can also analyze the electrophilicity of carbonyls to give us a sense for how reversible or how unfavorable is maybe another way to say that. So just to make sure that you can do this on your own, I'm going to give you a third structure. So it's going to be an aldehyde, but we're going to change the methyl group. So instead of a CH3, we'll have a CCl3 group. I'll draw all the chlorines in, and we'll try to hydrate this. So again, knowing the exact number, just looking at of an equilibrium constant for just this reaction, essentially not possible from a structural perspective, but you can make comparisons. So what I want you to do is to decide, well, the hydration equilibrium constant, so we're going to be making this structure here, where our chlorines are all still attached. Will the equilibrium constant for this reaction be larger than our other aldehydes, so greater than 1? Or will it be less? Or will it be about the same? So you're going to have to make some decisions here using this framework we're developing about carbonyl electrophilicity to guide you. So go ahead and pause your video and make that comparison now. You've had your chance to do your analysis, and you've made your prediction about the favorability of the hydration of this aldehyde relative to this one. So let's go through this together. When I look at these 2 structures, I notice that the hydrogens here are my right-hand substituents. Those are the same, and so any type of reactivity differences between this aldehyde and this one will be derived from the differences in a methyl and what's called a trichloromethyl group. So we know that methyl groups are hyperconjugative donors. But the trichloromethyl group is a bit different. We know that there are big bond dipoles that run from carbon to chlorine, and that makes this whole substituent a powerful inductive acceptor. Which should actually destabilize the carbonyl and make it more electrophilic. Once we notice that that's true, we could reliably predict that the hydration of this aldehyde should be much more favorable than this one. I have a more electrophilic carbonyl here. And so it turns out that that's true. Experimentally, if you measure the equilibrium constant, you find it's a kind of crazily large 10 to the 6th. So really, this aldehyde in the presence of water almost doesn't exist. You almost are entirely on the right-hand side of the equilibrium, so much so that this compound is called chloral for, it's kind of a cute combination of chlorine and aldehyde, hydrate. Because, well, we've just made a hydrate out of the combination of chlorine and aldehyde, right? So this compound, chloral hydrate, was discovered in the mid-1800s and started being used for a variety of applications. It was a very popular sedative and a mild anesthetic, so it was used for dental work almost all the way up, actually just past World War II, as well as for treating anxiety. It was actually a predecessor treatment to benzodiazepines, things like Valium, and was a drug of abuse in the mid-19th century all the way up until about World War II. It's also continuously used in laboratory work. So Hoyer's reagent, so for like botany sample fixing, is mostly chloral hydrate as well. And so some of the chemistry that we'll be learning about throughout the rest of this SLO is actually related to those kinds of microscopy and sample fixing types of techniques. Okay, so the big takeaway here, aside from the fact that chloral hydrate is pretty cool, is that what we can actually do in a case where nucleophile anion stability isn't helpful, so if we have like neutral nucleophiles, we can actually analyze the electrophilicities of carbonyls to make decisions about how favorable or how reversible these types of addition reactions are. And that's generally to say that as the electrophilicity of the carbonyl goes up, that the favorability of the addition also goes up. Okay, so that's essentially the other half of the model that we need to have. We should be able to analyze nucleophiles in terms of anion stability, but if we have neutral nucleophiles in these kind of cases, it's going to make a lot more sense to analyze the carbonyls themselves.